On behalf of the entire RSET team, we want to welcome you to part one of the introductory webinar, Satellite Remote Sensing for Agricultural Applications. Wherever you are joining us from, we hope you are staying safe and healthy. Today is the first part of a four-part introductory webinar series running every Tuesday starting today through May 5th. The four-part series will focus on data products, data access, and case studies on how remote sensing can be used for decision-making among the agriculture and food security communities. Today's webinar will provide an overview of agricultural remote sensing, focusing on the history, platforms and sensors, and applications of space-based Earth observations for agriculture and food security. Each webinar is 1.5 hours long, with a 1-hour presentation followed by roughly 30 minutes for questions and answers. Homework assignments will be available after parts 1 and 3 from the RSET website. Answers must be submitted via the Google form. The link to the homework is found on the website, and you can access it at the following link. The due dates for both homework assignments are April 28th and May 12th. A certificate of completion will be awarded to all attendees who attend all webinars and complete both homework assignments. You will receive a certificate approximately 2 months after the completion of the course from Marines Martin. The prerequisite for this webinar series is the Fundamentals of Remote Sensing, Sessions 1 and 2A. Both sessions are found on the RSET website and from the link below. The Fundamentals of Remote Sensing webinars are available for viewing at any time, providing basic information about satellite orbits, types, resolutions, sensors, processing levels, and specific applications. The following are the objectives for part 1 of this webinar series. By the end of this presentation, participants will identify which satellites and sensors can be used for agricultural applications, specific scientific data products that are appropriate for agricultural applications, and the limitations of remote sensing and modeled data for agriculture and food security. The outline for this webinar is as follows. We'll provide a brief background on the RSET program, an historical timeline of how Earth observations have been used for agriculture, specific satellites and sensors for agricultural applications, caveats and limitations of remote sensing, an introduction to the NASA Harvest program, and applications for satellite remote sensing for agriculture and food security. NASA's Applied Remote Sensing Training Program, better known as RSET, builds the skills to acquire and use satellite and model data for decision support. The program is part of NASA's Applied Sciences Capacity Building Program. The program seeks to empower the global community through online and in-person remote sensing training, covering topics related to air quality, disasters, land, and water resources. RSET's goal is to increase the use of earth science in decision-making through training for policymakers, environmental managers, non-governmental organizations, and professionals in the public and private sectors. All RSET materials are free and available for you to use and adapt for your audience. We request that if you use the materials, methods, and data presented in our trainings, please acknowledge the NASA Applied Remote Sensing Training Program. This infographic gives the timeline for RSET for its first 10 years from 2009 to 2019. Each bubble size corresponds to the number of attendees per training and application area. For RSET's first 10 years, the program held more than 130 trainings, with over 30,000 participants, joining both in person and online from across the planet. There has been a marked increase in the number of participants over the past 5 years. And regardless if this is your first training or your 10th, we thank all who participate in our webinars to learn more about how NASA Earth observations and Earth science can be used for better decision making. To learn more about RSET, please visit our website where you have access to all the previous trainings and materials. Now, for a brief background on the history of remote sensing in agriculture. The first successful low Earth orbital weather satellite was launched almost 60 years ago to the day by NASA and other partners on April 1st, 1960. Named the Television Infrared Observation Satellite 1, or TIROS-1, it was NASA's first experimental step to determine if satellites could be useful in the study of the Earth. Following the success of the TIROS program, NASA operated the Nimbus program, which were second-generation meteorological satellites used for collecting atmospheric science data in different spectral regions. The first of the Nimbus satellites, Nimbus 1, successfully launched on August 28, 1964. With the proven ability to observe Earth from space with multispectral instruments, a statement of agreement was signed between the U.S. Department of Agriculture and NASA in 1965. This interagency collaboration formally began remote sensing research with the USDA's Agricultural Research Service. The objectives were to characterize the reflectance and emission signatures of different land covers, both crops as well as rangeland, that would permit their identification using sensors on aircraft and satellite platforms. This research helped establish the scientific basis for using spectral properties to determine crop cover and plant growth development. This pioneering work helped lead to determining requirements for and use of the first multispectral sensors carried on Landsat-1, originally named the Earth Resources Satellite 1, whose platform was a repurposed Nimbus spacecraft. From winter of 1971 into the spring of 1972, a mega drought occurred across much of Europe, with Eastern Europe being hit particularly hard. The Soviet Union experienced widespread crop failure, and to prevent widespread hunger, they turned to international markets to make up for their shortfall. With accurate information as to the extent of the massive crop shortfalls in the Soviet Union, the US government negotiated a 3-year deal that allowed the Soviets to buy US grain on credit. Since Soviet negotiators were able to act quickly in securing credit before markets could adjust to the demand, the US inadvertently drove grain prices up dramatically and lost significant revenue by subsidizing the purchase instead of offering it at market value. This event is what's known as the Great Grain Robbery. Over time, markets adjusted to the worldwide grain shortfalls and increased demand, but it was too late to cause considerable disruption in global grain markets. If the US had timely spatial information to the extent of the Soviet crop shortfalls, the outcome could have been very different. The same year of the Great Grain Robbery saw the launch of Landsat-1, originally named the Earth Resources Satellite 1, which was the first civilian Earth observation satellite. Landsat-1 was an ambitious effort by the Department of Interior, NASA, and the USDA. The main instrument was the Multispectral Scanner, or MSS, which observed the Earth's landmass in 4 spectral bands. The satellite was launched with the express intent to study and monitor the planet's landmasses. And since the launch of Landsat 1 in 1972, the Landsat program has provided the longest continuous record of Earth's land surface observed from the vantage point of space. Requirements for the instrument were incorporated from research carried out by the interagency collaboration between NASA and USDA ARS in the mid to late 1960s. The use of Landsat satellite imagery for global agricultural monitoring began almost immediately after the launch of Landsat 1, making agricultural monitoring one of the longest standing operational applications for the Landsat program. For the first time, satellite-based remote sensing delivered global observations of crop response to weather-related phenomena in previously inaccessible parts of the world. With the advent of space-based agricultural monitoring, a joint undertaking was carried out by the USDA, NASA, and the National Oceanic and Atmospheric Administration. The Large Area Crop Inventory Experiment, or LACI, was carried out over 3 global crop seasons from 1974 to 1977 to demonstrate that multispectral imagery from satellites, together with meteorological data from NOAA satellites and from ground stations, could be used operationally to produce timely estimates of wheat area and wheat yield forecasts in the United States and in other major wheat growing regions of the world. The first phase of LACI focused on determining wheat area and yield in the U.S. Great Plains. The second phase focused on wheat area and yield in Canada and the former Soviet Union. The experiments used the 90-90 criterion, where at-harvest production estimate be within 10% of the true value with at least a 90% probability. The success of LACI proved an economically important application of multispectral remote sensing from space. At the same time as LACI in 1976, USDA's Agricultural Research Service was conducting their Wheat Yield Project. This was a multidisciplinary and multi-institutional group of scientists from the USDA ARS, NASA, Purdue's Laboratory for Applications of Remote Sensing, and elsewhere. The project was conducted across the United States in regions where wheat was the predominant crop. The Wheat Yield Project helped better the design of wide-band radiometers and infrared radiation thermometers for in-situ observations. It also began to develop remote sensing methods for assessing normal plant conditions and providing early warning of plant stress. The collective research made a linkage among remotely sensed crop parameters, development and yield models, and observations from satellites being used to estimate crop yields. Building on the successes of LACI and ARS's Wheat Yield Project, another joint program was sponsored by USDA, NASA, NOAA, and the USAID in 1980. The program was named the Agriculture and Resources Inventory Surveys through Aerospace Remote Sensing, or AgriSTARS for short. During the 4-year duration of the program, researchers sought to determine the feasibility of integrating remote sensing technology into existing and future USDA missions. The goal was to expand upon previous research with wheat to include monitoring of other commodity crops such as soybeans, maize, rice, cotton, and barley. Projects spanned from soil and crop condition assessments to early warning of plant stress, soil moisture measurements, and a better understanding of how electromagnetic radiation interacted with crops and rangeland. During the AgriSTARS project, a fundamental understanding of microwave remote sensing of soil moisture, particularly in the L and C band frequencies, was achieved using sensors on ground, aircraft, and satellite platforms. The scientific knowledge gained from AgriSTARS remains a foundation for research today. Since the launch of the first polar orbiting weather satellite in 1960, NOAA and the European Organization for the Exploitation of Meteorological Satellites, or EUMETSAT, have been funding a constellation of polar orbiting weather satellites to improve the accuracy of weather analysis and forecasting. Originally designed for meteorological applications, the Advanced Very High Resolution Radiometer, or AVHRR, instrument was launched on NOAA 6. It was the first time vegetation could be monitored globally from a satellite platform with a daily revisit time. The first 3 Landsat missions had a revisit time of 18 days. A major advantage of daily global coverage is it minimizes the effects of cloud cover and other unfavorable atmospheric conditions. The 40-year history of AVHRR on subsequent NOAA missions provides a historical context for long-term monitoring and comparison of land surface conditions, from vegetation health to drought frequency and extent. Now that we've covered some history, let's go over why satellites are useful for agricultural applications. Some examples are below. Satellites provide timely, objective, local, regional, to global coverage. They are useful for observing regions of the planet that are inaccessible. They can be used to monitor plant growth and estimate crop productivity. They can be used to assess soil moisture and irrigation requirements, identify soil and crop characteristics and conditions, better forecast precipitation and crop disease, maximize crop yields while reducing energy consumption, avoid waste of farm inputs such as water, fertilizer, and pesticide. And these are societal and economic benefits that can better inform the public, private, and non-governmental sectors. Some of the main applications of satellite remote sensing for agriculture and food security are crop monitoring, which includes crop phenology, which is the start of season, peak of season, and end of season, crop area, crop type, crop condition, yield, irrigated landscape, flood, drought, frost, and accurate and timely reporting of agricultural statistics. Crop forecasting, which is the accurate forecasting of yield or shortfalls in crop production and food supply per region and per country. Another application is for market stability. Remote sensing can be used to lower uncertainties and increase the transparency of global food supply. It also reduces price volatility by anticipating market trends with reduced uncertainty. Another application is for humanitarian aid. Remote sensing can be used to monitor food security in high-risk regions worldwide and provide early warning of famine, enabling the timely mobilization of an international response in food aid. Some of the biophysical and geophysical characteristics of vegetation that can be derived empirically from remote sensing vegetation indices are as follows: chlorophyll content, above ground biomass, the leaf area index, which is a one-sided green leaf area per unit ground area in broadleaf canopies, photosynthetic primary production, the fraction of absorbed photosynthetically active radiation. These biophysical characteristics help to quantify the density, extent, and the health of vegetation. This next section will cover specific satellites and sensors for agricultural applications. The following table is a list of the satellites, sensors, and analysis-ready scientific products we'll be covering in today's webinar. For a comprehensive list of all current and future NASA assets useful for agricultural applications, we've prepared a PDF which can be found on the webpage for this training, as well as from the link below. We encourage you to refer to the supplementary document for more information on all the material covered over the course of these webinars. The first analysis-ready scientific product we will discuss is land surface reflectance. Land surface reflectance provides an estimate of surface spectral reflectance as measured at ground level by accounting for atmospheric effects like aerosol scattering and thin clouds. It is a ratio of surface radiance to surface irradiance, and as such it is unitless and typically has values between 0 and 1. It allows for quantitative comparisons of satellite images acquired under widely varying atmospheric conditions for consistency and repeatability. Land surface reflectance is useful for measuring the greenness of vegetation, which can then be used to determine phenological transition dates, including start of season, peak of season, and end of season. Land surface reflectance is an input for generation of several land products, such as vegetation indices, bidirectional reflectance distribution function, thermal anomalies, snow and ice, fraction of absorbed photosynthetically active radiation, and leaf area index. Land surface reflectance is useful for measuring the greenness of vegetation, which can then be used to determine phenological transition dates. The first instrument we'll discuss for land surface reflectance is a moderate resolution imaging spectroradiometer, or MODIS. It is a 36-band spectroradiometer measuring visible and infrared radiation. The first MODIS instrument was launched on board the Terra satellite in December 1999, and the second was launched on the Aqua satellite in May of 2002. Both satellites are operated by NASA. The MODIS instruments on Terra and Aqua image the same area on Earth approximately 3 hours apart, observing the entire Earth's surface every 1 to 2 days. These sensors work in tandem to optimize cloud-free surface viewing and provide opportunities to investigate processes that occur on sub-daily timescales. Their orbit is sun-synchronous, meaning that the satellite always passes over a particular part of the Earth at about the same local time each day. The spatial resolution of the MODIS instrument is 250 meters at nadir for 2 bands, 500 meters at nadir for 5 bands, and the remaining 29 bands at 1 kilometer. The MODIS data is processed to a range of analysis-ready science products with the temporal resolution of daily, 8-day, 16-day composites, monthly, and yearly. MODIS imagery is used to derive atmosphere products, land products, cryosphere products, as well as ocean products. A time series of these scientific products dates from 2000 to the present. MODIS products are processed to levels 2 and 3 with a product name of MOD for Terra-derived data and MYD for Aqua-derived data. In this case, for the sake of this webinar, the MOD prefix should be taken as referring to the dataset in general. The surface reflectance products are an estimate of the surface spectral reflectance for each band as it would have been measured at ground level, corrected for atmospheric conditions such as gases, aerosols, and Rayleigh scattering. The user's guide we provide, the link to, details the product descriptions, data product quality, details on the atmospheric correction algorithm, and other known problems. You can read more about each analysis-ready land surface product and acquire daily and 8-day composites from NASA's Earth data. The chart below shows many of the MODIS land products, along with the short name for each product, the spatial resolution, as well as the temporal resolution. All MODIS land products are processed at levels 2 to 4. Level 0 data is raw satellite feeds. Level 1 has been radiometrically calibrated, but not otherwise altered. Level 2 data is level 1 data that has been atmospherically corrected to yield a surface reflectance product. Level 3 data has been gridded into a map projection and usually has also been temporally composited or averaged. And level 4 data is modeled output using lower level variables. The next instrument we'll discuss for land surface reflectance is the Visible Infrared Imaging Radiometer Suite, or VIIRS. VIIRS was first launched as one of 5 instruments on the Suomi National Polar Orbiting Partnership, or Suomi NPP, mission in 2011. This multispectral imager obtains daily observations from the visible wavelengths through the thermal. The instrument was designed in part to provide continuity with the MODIS instrument and has many of the same characteristics for land monitoring. The Suomi NPP mission, shared by NASA and NOAA, is a bridging mission to the Joint Polar Satellite System, VIIRS instruments. NOAA 20 was launched on November 18, 2017, and is the first of 4 VIIRS instruments in the JPSS series. VIIRS observes the entire Earth's surface twice each day. The 3,000 kilometer swath width of the VIIRS instrument, which is 710 kilometers greater than that of MODIS, allows for no gaps in coverage, which are observed in MODIS near the equator. The VIIRS instrument provides 22 spectral bands at 2 spatial resolutions, 375 meters and 750 meters, which are resampled to 500 meters, 1 kilometer, and 0.05 degrees as NASA data products to promote the consistency with the MODIS heritage. Unlike MODIS, VIIRS maintains a uniform pixel size across the scan by resampling. Imagery has been collected from 2012 to the present. VIIRS land surface reflectance products build on the heritage of land science started with AVHRR and MODIS. Products are resampled to 500 meters, 1 kilometer, and 0.05 degrees to promote consistency with MODIS products. The tile numbering scheme and boundaries for VIIRS products are the same as they are for MODIS. The data are corrected for atmospheric conditions, such as the effects of molecular gases, including ozone and water vapor, and for the effects of atmospheric aerosols. We've provided a link to the Surface Reflectance User's Guide to answer any questions you may have on the products and how they're generated. The last link takes you to the NASA Earth Data website, where you can download VIIRS land surface reflectance products and learn more about each product. As stated before, VIIRS was intended to provide continuity to the AVHRR and MODIS missions. There are many similarities between the MODIS and VIIRS instruments, but we thought it important to describe a few of the differences. For example, there are similar but not identical spectral characteristics, as seen in the chart on the right. VIIRS also has improved spatial resolution at swath edge. For more information on the similarities and differences between the two sensors, in context of calculating vegetation indices for agricultural monitoring, we've provided the following reference for Skakun, Justice, Vermote, and Roger. Another important resource for land surface reflectance is the Landsat Data Continuity Mission, or Landsat 8. Landsat satellites, as we mentioned before, have been operating continuously since 1972, when the first Landsat satellite was launched. In February 2013, NASA successfully launched the most recent Landsat satellite, Landsat 8. And in May 2013, operational control was given to the U.S. Geological Survey, or USGS. Currently, 2 Landsat satellites are operational, Landsat 7 and Landsat 8. Landsat 7 has a technical issue that results in missing data in each scene, which at times limits data uses. Landsat 8 is currently collecting hundreds of complete, high-quality scenes every day. Landsat 8 carries 2 instruments, the operational lambda imager and the thermal infrared sensor. The OLI instrument collects visible, near-infrared, and shortwave infrared images of the Earth with a 16-day repeat time. The USGS offers on-demand production of Landsat 8 operational land imager and thermal infrared sensor land surface reflectance data through their Earth Explorer website. The link is provided at the bottom of the following slide. The surface reflectance products are generated at the Earth Resources Observation and Science Center, or AROS, at a 30-meter spatial resolution. The AROS Science Processing Architecture on-demand interface corrects satellite images for atmospheric effects to create Level 2 data products. The data is free to request, but you must have an account registered with the AROS registration system. AROS also provides analysis-ready data product, which includes surface reflectance data for the conterminous United States, Alaska, and Hawaii. These are also available from the Earth Explorer website, which is provided on the following slide. The Operational Land Imager, or OLI, has a moderate spatial resolution of 30 meters with a 15-meter panchromatic band. Spectral resolution consists of 9 bands comprising the visible, near-infrared, and shortwave infrared wavelengths. The revisit time is 16 days, which can be a challenge if the conditions are cloudy. Level 2 surface reflectance data products can be acquired from the Earth Explorer link below as either on-demand or analysis-ready data products. The Sentinel-2 mission is a land monitoring constellation of 2 satellites that provide high-resolution optical imagery. The mission has been developed and operated by the European Space Agency. The mission provides a global coverage of the Earth's land surface every 10 days at the equator with 1 satellite and every 5 days at the equator with 2 satellites. The multispectral imager instrument is the primary sensor on both satellite Sentinel-2A and Sentinel-2B, offering high-resolution optical imagery in 4 bands at 10 meters, 6 bands at 20 meters, and 3 bands at 60 meter spatial resolution. Sentinel-2A launched in 2015, and Sentinel-2B launched in 2017. The global acquisitions of high spatial resolution multispectral images with a high revisit frequency make the bottom of atmosphere products very useful for crop type classification, detection of tillage, yield modeling, and multi-sensor fusion. The 3 bands, bands 5 to 7, that capture vegetation red edge at 20 meter spatial resolution are especially useful for agriculture and vegetation applications. The Level 2A product provides orthorectified bottom of atmosphere reflectance and can be acquired at the link provided at the bottom of the slide. The data is free, but you have to register an account with Copernicus. One of the biggest innovations in moderate resolution multispectral satellite measurements has been the harmonized Landsat 8 and Sentinel-2 products, or HLS for short. The HLS project is an effort to harmonize the data of the 2 satellite programs, both Landsat and Sentinels, so they can be more easily used in unison. The ultimate goal is to obtain seamless 2 to 3 day surface reflectance coverage at 30 meters that removes residual differences between the sensors due to spectral bandpass and view geometry. The 30-meter resolution with 2 to 3 day revisit time using both products is critical for timely agricultural monitoring at the field scale. HLS products have been gridded to a common pixel resolution, map projection, and tile. They've been atmospherically corrected and cloud masked. They've also been normalized to a common nadir view geometry via bidirectional reflectance distribution function estimation. In the latest version of HLS, all of North America and some globally distributed sites have been processed. A current map of HLS coverage is provided on the right side of the slide. The research project combines the land surface observations of OLI and MSI into 2 data products, L30 and S30. The L30 product consists of surface reflectance derived from all Landsat 8 Level 1 products. Products are gridded with the Sentinel-2 tiling scheme and include a nadir adjustment. The S30 product consists of surface reflectance derived from the Sentinel-2 MSI Level 1 data. Products are resampled to 30 meters and include nadir adjustment and spectral adjustment. HLS surface reflectance products can be acquired from the link at the bottom of the slide. The next scientific product we'll discuss is evapotranspiration. We'll be going into much more detail on this topic in week 4 of this webinar series, so be sure to attend all 4 sessions. Evapotranspiration is the sum of evaporation from the land surface plus transpiration in vegetation and soils. It's highly variable in space and time, which is why remote sensing has long been recognized as the most feasible means to provide spatially distributed regional evapotranspiration information over land surfaces. It is a critical component of the water and energy balance of climate, soil, vegetation interactions. Evapotranspiration is extremely useful in monitoring and assessing water availability, drought conditions, and crop production. Evapotranspiration, or ET, cannot be measured directly with satellite instruments. It's calculated through modeled outputs which are dependent on many variables, such as land surface temperature, air temperature, solar radiation, humidity, albedo, soil conditions, and vegetation cover. The link provided below is from a previous RSET training on evapotranspiration. We encourage you to go through the materials found on the webpage and join us for part 4 of the webinar on May 5th, where we'll be going into greater detail on evapotranspiration and the evaporative stress index used for agricultural applications. The following image is a simplified infographic for evapotranspiration and the water and energy balance of weather, soil, vegetation interactions. The MODIS evapotranspiration project estimates global terrestrial evapotranspiration from Earth's land surface by using satellite remote sensing data. With Mode 16, the effects of changes in climate and land use on regional water resources and land surface energy change can be quantified. The Mode 16 global evapotranspiration latent heat flux datasets are 500-meter land surface products at 8-day and annual intervals. The dataset covers the time period from 2001 to the present. The algorithm used for the Mode 16 Level 4 data product collection is based on the logic of the Penman-Monteith equation, which includes inputs of daily meteorological reanalysis data along with MODIS products such as vegetation property dynamics, albedo, and land cover. Included is a link to the Mode 16 User's Guide and access to the Mode 16 Evapotranspiration Collection on NASA's Earth Data Search portal. The Ecosystem Spaceborne Thermal Radiometer Experiment, or EcoStress, on the International Space Station measures the temperature of plants to better understand how much water plants need and how they respond to stress. EcoStress was launched to the ISS on June 29, 2018. It has a viewing swath width of around 384 kilometers and views the surface of the Earth from 53 degrees north latitude to 53 degrees south latitude with variable revisit times dependent on the orbit of the International Space Station. EcoStress addresses 3 overarching science questions. How is the terrestrial biosphere responding to changes in water availability? How do changes in diurnal vegetation water stress impact the global carbon cycle? And how can agricultural vulnerability be reduced through advanced monitoring of agricultural water consumptive use and improved drought estimation? EcoStress Level 3 products contain evapotranspiration data derived from Level 2 data. The Level 4 products contain evaporative stress index and water use efficiency derived from the Level 3 data. Originally, EcoStress coverage was limited to the conterminous United States, key agricultural zones, and selected FluxNet sites, but evapotranspiration Level 3 data is now available for the planet between 53 degrees south latitude and 53 degrees north latitude. The link at the bottom of the page takes you to an RSET training specifically on the EcoStress mission where you can learn more. The spatial resolution for the level 3 evapotranspiration products is 70 meters, but the revisit time is variable depending on the orbital path of the International Space Station. EcoStress Science Data Systems will deliver levels 0 through level 4 data products to the United States Geological Survey AROS Center for archival and public distribution. Level 3 and 4 products can be searched and acquired through NASA's Earth Data Search from the link below, as well as e-learning opportunities provided by the USGS to work with EcoStress data. The last resource we'll discuss for the evapotranspiration is the Land Data Assimilation System, or LDAS. The aim of LDAS is to produce high-quality fields of land surface states, for example, soil moisture and temperature, and fluxes, such as evapotranspiration and runoff, by integrating satellite and ground-based observational data products using advanced land surface modeling and data assimilation techniques. LDAS provides model-based evapotranspiration data, of which there is a global collection called GLDAS and a North American collection called NLDAS. The spatial resolution of the data is 0.25 degrees and 1 degree. The temporal resolution is 3 hourly, daily, and monthly. Part 2 of this webinar series will focus on LDAS data for soil moisture, so we hope you would join us next week to learn how to analyze the data specifically for soil moisture applications. Below is a link for acquiring LDAS evapotranspiration data. Land surface temperature is another science product derived from Earth observations. Land surface temperature products show the temperature of the land surface in degrees Kelvin. Land surface temperature differs from air temperature measurements as it provides the temperature of whatever is on the surface of the Earth, for example, bare sand, ice, snow-covered area, leaf-covered tree canopies, roads, etc. The land surface temperature is useful for monitoring changes in weather and climate patterns. It is used in agriculture and water resources management to allow farmers and decision makers to evaluate water requirements. One of the land products provided by the MODIS team is land surface temperature and emissivity, which is designated by the product name of Mode 11. Mode 11 is a level 3 product available from both Terra and Aqua satellites. There are several products created for both satellite platforms ranging from daily, 8-day composites, and monthly composites, which is a simple average of all the corresponding values from the land surface temperature values collected during that period. The spatial resolution varies from 1 kilometer, 6 kilometers, and 0.05 degrees. Products from Terra are available from 2000 to the present, and those from Aqua platform from 2002 to the present. Below are links provided for the Mode 11 User's Guide to learn more about how the algorithms and the products were developed, as well as a link to the NASA Earth Data Search to explore the data sets and download the data. Another sensor that is used to derive land surface temperature is the VIIRS sensor flown on Suomi NPP. The VIIRS land surface temperature and emissivity algorithm and data products are developed synergistically with the MODIS collection land surface temperature and emissivity algorithm and data products to ensure continuity and enable development of consistent, long-term, and well-characterized climate data records from NASA's Earth Observing System satellites, from them to the JPSS platforms. The temporal resolution of the science products is 750 meters and 1 kilometer. Global data coverage can be acquired from the VIIRS sensor from 2012 to the present. The links below provide more description of the algorithms and how the data products were created, as well as a link to the NASA Earth Data Search, where data can be explored and downloaded. Arguably, the most important agricultural weather parameter is precipitation. Precipitation is a key component of the water cycle and difficult to measure since rain and snow vary greatly in both space and time. Satellites provide frequent and accurate observations and measurements of rain and snow around the planet, especially where ground-based data are sparse. Radiometer estimates measure the intensity and variability of latent heating structures of precipitation systems. The agricultural community needs to know the timing and amount of rain or snow to forecast crop yields, as well as freshwater shortages affecting irrigation and production. NASA's Precipitation Measurement Missions, or PMM, provide a continuous, long-term record over 20 years of precipitation data. The Global Precipitation Measurement Mission is a joint mission between NASA and the Japan Aerospace Exploration Agency, or JAXA. The satellite was launched February 27, 2014, and operates as the core satellite within a constellation of international meteorological satellites. GPM has been integrated with data from global constellation of satellites to yield improved spatial temporal precipitation estimates. The Integrated Multi-Satellite Retrievals for GPM, or iMerge, provides data products at half-hourly, daily, and monthly. Multiple runs accommodate different user requirements for latency as well as accuracy. iMerge precipitation products are georeferenced to a 0.1 degree grid and are available to access from 2000 until the present. RSET held an advanced 3-part webinar on using iMerge data for calculating precipitation anomalies, which can be found at the bottom of the slide. We've also provided a link to explore and download iMerge products from the NASA Earth Data Search. Another precipitation product derived from satellite data is the Climate Hazard Group Infrared Precipitation with Station Data, or CHIRPS. CHIRPS was developed by the Climate Hazard Center at UC Santa Barbara. Rainfall estimates are made from rain gauge and satellite observations, incorporating in-house climatology, 0.05 degree resolution infrared satellite data, and in situ station data. Two strengths of CHIRPS data are the higher spatial resolution and long time series. The spatial resolution is 0.05 degrees from 50 degrees south latitude to 50 degrees north latitude, and rainfall estimates can be acquired from 1981 to the near present. Data can be accessed from the link at the bottom of the slide. Soil moisture is important for surface hydrology studies, as it controls the amount of water that can infiltrate the ground, replenish aquifers, and contribute to excess runoff. Current ground measurements of soil moisture are sparse and have limited coverage. Satellite data helps fill in those gaps. The Soil Moisture Active-Passive, or SMAP mission, is an orbiting observatory that measures the amount of water in the surface soil globally. The mission launched in January 2015. SMAP helps provide information on water availability and environmental stress for estimating plant productivity. Observed variations in soil moisture, regardless of the data resolution, correlate very well with variations in crop yield. SMAP data is used to model soil moisture using an L-band passive radiometer. Level 4 products assimilate SMAP L-band brightness temperature data into a land surface model generating root zone and surface soil moisture at a 9-kilometer spatial resolution. Next Tuesday, a lot of the webinar will be focused on SMAP science and applications for soil moisture, so please join us next week for this exciting webinar. Another NASA source for soil moisture is the Land Data Assimilation System, or again, LDAS. LDAS uses numerical models to integrate satellite information with ground-based data for soil moisture estimates. Next week's webinar is entirely focused on soil moisture, with examples of how to access and perform analysis using LDAS soil moisture data. We do hope you will join us next week. Vegetation indices are robust empirical measures of vegetation activity at the land surface. They are designed to enhance the vegetation reflected signal from measured spectral responses by combining two or more wavebands. Healthy vegetation absorbs blue and red light to fuel photosynthesis and create chlorophyll. A plant with more chlorophyll will reflect more near-infrared energy than an unhealthy plant. Thus, analyzing a plant's spectrum of both absorption and reflection in visible and in near-infrared wavelengths can provide information about the plant's health and productivity. Reflected near-infrared radiation can be sensed by satellites, allowing scientists to study vegetation from space. One commonly used vegetation index is the Normalized Difference Vegetation Index, or NDVI, which takes the difference between the near-infrared and red reflectance divided by their sum. Low values of NDVI generally correspond to barren areas of rock, sand, exposed soils, or snow. Increasing NDVI values indicate greener vegetation, including things like forests, croplands, and wetlands. Some advantages of NDVI are it's an efficient and simple index to identify vegetated areas and their condition. NDVI reduces sun angle, shadow, and topographic variation effects. It also enables large-scale vegetation monitoring, allowing comparison of different regions through time. The formula shows how to calculate NDVI from near-infrared and red bands. This equation can be calculated from all the multispectral land surface products we discussed earlier in the webinar. Theoretically, values range from -1 to 1. The typical range of NDVI measured from Earth's surface is between about -0.1 for non-vegetated surfaces and as high as 0.9 for dense green vegetation. The index increases with increasing green biomass. The index changes seasonally and responds to climatic conditions. Most crop monitoring and forecasting methodologies use vegetation indices like NDVI in their analysis. Some of the agricultural applications of NDVI are its ability to monitor phenology. NDVI can be a good drought indicator, as well as assessing vegetation health in a field or on a rangeland. It's also useful for carbon monitoring, as well as deriving the leaf area index. MODIS vegetation indices products, also referred to as the product name Mode 13, provide consistent spatial and temporal time series comparisons of global vegetation conditions that can be used to monitor the Earth's terrestrial photosynthetic vegetation activity. Gridded vegetation index maps depicting spatial and temporal variations in vegetation activity are derived at 16-day and monthly intervals in support of accurate seasonal and interannual monitoring of the Earth's terrestrial vegetation. Two vegetation indices products are made globally for land regions. The first product is NDVI, which is referred to as the continuity index to the existing NOAA AVHRR derived NDVI. There is currently around a 40-year NDVI global dataset from 1981 to 2020 from the NOAA AVHRR series, which in conjunction with MODIS data provide a long-term data record for use in operational monitoring studies. The second vegetation index product is the Enhanced Vegetation Index, or EVI, with improved sensitivity over high biomass regions, such as the tropics. The two vegetation indices complement each other in global vegetation studies and improve upon the extraction of biophysical parameters. NDVI and EVI are retrieved from daily, atmosphere-corrected, bidirectional surface reflectance. The spatial resolution of NDVI and EVI products are 250 meter, 500 meter, and 1 kilometer. The temporal resolution of these products are 8-day, 16-day, monthly, from 2000 until the present. Both the Mode 13 product user's guide and the link to the NASA Earth Data Search are below for data exploration and downloading. VIIRS is building on the ongoing, roughly 40-year-old NDVI time series of AVHRR and will expand on the 20-year MODIS Enhanced Vegetation Index time series. The VNP13 product provides 3 primary vegetation layers: NDVI, EVI, and EVI2. EVI2 is a modified EVI, or Enhanced Vegetation Index, that eliminates dependency on the blue band and addresses some of the operational EVI issues. Level 3 spatial and temporal gridded vegetation index products are composites of daily surface reflectance. They are generated at 500 meter, 1 kilometer, and 0.05 degrees every 16 days, and as well as the calendar month. Both the user's guide and link to download the data products are provided below. Vegetation indices can be calculated from several of the OLI bands on Landsat 8. Landsat surface reflectance derived NDVI are produced on demand from USGS AROS from the link provided below. You can also calculate vegetation indices using QGIS or other software. Instructions on how to do so can be found at the link from the following RSET training. Excuse me. Like surface reflectance products, the spatial resolution of NDVI products is 30 meters with a revisit time of 16 days. Global coverage of vegetation indices calculated from OLI bands run from 2013 to the present. The last option we'll discuss for deriving vegetation greenness from vegetation indices is from the multispectral instrument flown on Sentinel-2A and 2B. Vegetation indices can be calculated using QGIS, SNAP, Google Earth Engine, or other image processing software. The spatial resolution of these vegetation products from MSI is 10 meters, and the temporal resolution is 5 days with both satellites. The Sentinels provide global coverage from 2015 to the present. The website to access Sentinel-2 data can be found at the link below. Over the past decade, synthetic aperture radar, or SAR, is playing an increasing role in agricultural monitoring. Agriculture and Agri-Food Canada now uses an integration of optical imagery and RadarSat-2 data operationally for the National Crop Inventory. Research has shown SAR data can be used for early season crop identification, quantitative estimation of production indicators such as leaf area index and biomass, phenology, temporal crop condition monitoring, and risk factors for crop disease. Some of the advantages of SAR data over optical data are provided below. SAR is a nearly all-weather capability and can be used and can be imaged day or night. Different microwave frequencies can penetrate through the vegetation canopy and through the soil. There are minimal atmospheric effects to SAR data. And SAR data is sensitive to dielectric properties, which are liquid versus frozen water in the substrate, as well as soil structure. Some of the disadvantages are the information content is different than optical data and sometimes difficult to interpret. There are speckle effects to contend with, as well as there are challenges with effect to topography, depending on your study area. With optical data, energy reflected by vegetation is dependent on leaf structure, pigmentation, and moisture. Products are available from visible to infrared wavelengths, consisting of several bands of data. Optical sensors only see surface tops because the canopy blocks the understory, limiting the inferences of land cover and land use to only when these are correlated well with the characteristics of top layers. With radar data, microwave energy scattered by vegetation depends on the structure, which is the size, density, and orientation, as well as the dielectric properties of the target. Radar signals are typically only at a single wavelength for each sensor. The signal can penetrate through the canopy, which is wavelength dependent, providing information on soil conditions or inundation state. There are two important things to remember about wavelength. The first is that the longer the wavelength, the greater the penetration through the medium, and second, that the length of the wave will determine the interaction with the surface objects. The wave will interact with objects that are approximately its size. The figure on the left shows the extent of penetration through different mediums with different bands. In vegetated areas, X-band is generally governed by the top of the canopy. C-band penetrates further, and L-band tends to penetrate deeply into the vegetation. Likewise, in the case of a dry, bare soil, X-band only sees the top surface of the soil, while L-band penetrates into the soil. Also, the wetter the soil, the less the penetration. There is a preferred wavelength depending on the type of study that you are conducting. The table on the right lists some of these. For example, the P-band is good for studies involving penetration through high biomass forests, such as those found in the tropics, and for assessing biomass. The P-band also penetrates deeper into soils and is good for assessing soil moisture at deeper levels than that provided by other shorter wavelengths. The L-band is also a good sensor for forest studies. The C-band and X-band are better for agricultural studies. There's currently no operational, freely available L-band data, and there's no P-band sensor in space. However, in 2021, NISAR will be launched, which is a joint NASA and Indian Space Agency L-band and S-band satellite. Also, in 2021, the European Space Agency will launch Biomass, which is a P-band satellite sensor. A new era of environmental monitoring with SAR imagery started with the launch of the first Sentinel satellite developed by the European Space Agency. Sentinel-1 is the first of the 5 Sentinel missions that ESA is developing for the Copernicus Initiative. The mission is composed of a constellation of 2 satellites, Sentinel-1A and Sentinel-1B, sharing the same orbital plane. The mission includes C-band imaging operating in 4 imaging modes with different resolutions down to 5 meters. It provides dual polarization capability with revisit time every 12 days. Sentinel-1 imagery has been acquired from 2014 to the present and can be accessed from the Alaska Satellite Facility as well as the Copernicus Open Access Hub. Links to both of these sites can be found below. Several RSET webinars have also covered SAR data, including data acquisition and analysis specifically for agricultural applications. We've provided those links below, and we highly encourage you to review these materials to learn more. The Sentinel-1 Toolbox is a free and open source software developed by the European Space Agency for processing and analyzing radar images from the Sentinel series of satellites, including Sentinel-1 SAR and SAR data from other satellites as well. The tool includes tools for interferometry, data analysis, and classification. It is really a great resource and very straightforward to use. It can be accessed through the link provided below. The previous sections of the webinar provided many of the science products and applications of satellite remote sensing for agriculture. The following section highlights some of the caveats and limitations of remote sensing data and products. As no instrument can do it all, it is difficult to obtain high spectral, high spatial, and high temporal resolution with the same instrument. Optical sensors cannot penetrate clouds or vegetative cover, which can lead to data gaps or a decrease in data utility. In regards to spatial resolution, while coarse resolution data, such as VIRS or MODIS, provides a synoptic view, the spatial resolution is too coarse for field-level assessments. In regards to temporal resolution, many satellites only pass over the same spot on Earth every 3 to 5 days, and sometimes as seldom as every 16 or more days. This can affect one's ability to assess crop conditions during critical times of the growing season. In regards to the limitations of spectral resolution, multispectral instruments observe reflected and emitted light in broad wavelength ranges for a particular band with a limited number of bands. The solution is a space-based hyperspectral instrument, but currently there are no freely available and operational hyperspectral sensors on a space-based platform. They currently only exist as aerial sensors, which are flown on airplanes, such as NASA's AVERIS instrument. Another limitation is large amounts of data exist in various file formats, file sizes, and from multiple sources, making it difficult and seemingly unwieldy to use for analysis. And finally, the knowledge of data and knowledge of tools is required to work with satellite data. There is a learning curve involved, which is one of the reasons that the RSET program exists. We're here to empower the global community through these online and in-person remote sensing trainings. Switching gears now, I want to tell you about an exciting program NASA launched in November of 2017. The NASA Harvest program is NASA's food security and agriculture program. Harvest is a consortium of more than 45 multidisciplinary and multisectoral actors from around the world, led and implemented by the Harvest Hub at the University of Maryland. The consortium brings together world-renowned experts working on environmental, economic, and social aspects of agriculture in universities, research centers, industry, space agencies, humanitarian organizations, ministries of agriculture, and more. Harvest is enabling and advancing awareness, use, and adoption of satellite Earth observations by public and private organizations to benefit food security and agriculture in the US and worldwide. One of the strengths of Harvest are their projects are driven by stakeholder and end user needs. The consortium is focused on operational research and development and the transition of those. They're demonstrating socioeconomic benefits of Earth observations for agriculture and food security and are NASA's contribution to the GeoGLAM task. We encourage you to go to the Harvest website to learn more about how the program is advancing the adoption of satellite Earth observations by public and private organizations. This infographic describes the impact areas, method areas, focus areas, innovation pathways, and facilitating mechanisms of the Harvest program. You can see it is a very strategic and all-encompassing approach to advance Earth observations for public and private benefit. Public-private partnerships, or PPP, has emerged as a high-priority innovation mechanism for reaching Harvest's goals. They have strong partnerships with the private sector and serve as a bridge to convene researchers, public, and private stakeholders. Below are some highlights from 2019 of the successes Harvest has achieved in public-private partnerships. Again, we highly encourage you to go to their website and follow them on social media to learn more about this exciting and innovative program. Included are some references to learn more about satellite remote sensing for agricultural applications. Next Tuesday, April 21st, Erica Podest and Amita Mehta will lead the webinar on soil moisture for agricultural applications. As a reminder, the homework assignment for Part 1 is available on the RSET webpage for this training, and answers must be submitted by Google Form by April 28th. This concludes the presentation part of this webinar. We will now transition to the question and answer session. Please enter your questions in the question and answer box. We will post the questions and answers to the training website following the conclusion of this course. If you have any questions following this webinar, feel free to contact myself and my colleagues at the emails provided below. Well, thank you all who have started to submit your questions. We hope that we will receive more. I guess we'll start at the top with question 1. Which is the most suitable sensor to measure the degradation of a grassland? So currently, most of the research monitoring grasslands involves the MODIS instrument, which we discussed earlier in the webinar series. And that is currently on the Terra and Aqua satellites. It gives a good course. It gives a coarse spatial resolution of 250 meters to 1 kilometer, and this is applicable for grassland biomes, which are usually quite large landscapes in terms of space. The other positive thing is they have a repeat time of 1 to 2 days, and because they're able to derive vegetation index products like NDVI, they're useful in calculating anomalies due to the long time series of MODIS data, which is currently 20 years. So a link that we're providing below is to the GeoGlam wrap, which is one of the programs within GeoGlam, and that is a program which is specifically dedicated to assessing rangeland productivity. And one of the tools that they use is an online spatial platform that you can use and interact with to monitor conditions within these the rangeland and pasture environments. So question 2, by what technique can the products of different sensors be merged? There are a number of different methods that researchers use, some of which will be discussed in the 4th part of this webinar series when Dr. Christopher Hain goes over evapotranspiration. So he will be going into greater detail on some of his methods. We're providing some publications below, and a good example was from the Harmonized Landsat Sentinel mission, in which we discussed earlier in the webinar. We've provided a link to that so you can learn more about how they fused optical data from different sensors. And the other link below is an example of fusing radar with optical data, which we've provided the link to below. Some of the challenges of fusing different remotely sensed data have to do with different code registration and normalization of different parameters. But we hope you'll explore some of these links that we're providing, and hopefully we'll get some more links provided as we before we put this on our webpage. So question 3, are you going to cover SMOS? SMOS is the Soil Moisture and Ocean Salinity Mission, and we will not be, I'm sorry, give me 1 second here. I'm sorry about that. So no, we will be not be covering the SMOS mission again, which is the it's a European Space Agency mission, which, similar to SMAP, uses a passive L-band radiometer. And we provided a link below so you can learn more about it, as well as accessing data from this mission. But no, we will not be covering it during this webinar series. So question 4, will this series cover remote sensing applications in the early warning system of vector-borne diseases? This webinar series will not. We will be focusing on crop monitoring with optical data. We'll be discussing soil moisture and evapotranspiration, but we are providing some links below that hopefully you can learn about how remote sensing data is being used for those specific applications. Question 5, is it possible to merge radar and optical sensor products? Yes, it is very much possible. We've provided a link below for a case study in Myanmar where they're monitoring rice with both Sentinel-1 C-band radar, which we discussed earlier in the webinar, as well as Landsat data. And so we hope you will explore and learn about some of the methods that were applied in that research project, and we hope to provide more examples when we post this to our webpage later this week. Question 6. Of the SNAP program in all its versions, the toolbox soil moisture has been removed. How can you install the toolbox soil moisture? I cannot answer that right now, but I will look into that, and we will post the solution or the answer to this later this week when we upload it to the training page for this web page. So stay tuned, and we hope to give you an answer soon. It looks like Brock is typing. Okay, great. Thank you, Brock. Also, our trainer next week, Dr. Erica Podest, hopefully she will be able to address that as well. So question 7, is any available free data that could be used to monitor vegetation regeneration in a very precise scale as we do with a LiDAR? So SAR imagery can be applied for monitoring stages of vegetation growth, and it has a relatively high spatial resolution at 10 meters. So that could be very valuable for monitoring vegetation growth, but it really depends at the scale in which you're intending to monitor that growth. For a much coarser resolution, there is a mission that launched quite recently, actually, in the last, I believe it was last year, named ICESat-2, and that uses a laser altimeter to map forest height, as well as ice sheet thickness and sea ice. So that could be potentially applicable to the type of research that you're trying to conduct. But again, it really depends on the scale in which you're trying to monitor vegetation regeneration. There's a number of methods that are out there, and we hope to provide some links to those before we upload it to the RSET webpage. So question 8, I believe we've already covered that one. Question 9, what is the difference between top of atmosphere and raw satellite imagery? Top of atmosphere correctance has been corrected radiometrically, and it is the light that's collected as it appears from the top of the atmosphere. Raw satellite data has not had any corrections to it, time corrected or georeferencing, as well as radiance corrected. So it's a different level product with some corrections that have been applied, and we will provide more information to that and more complete the answer to that before we upload it to the website, as well as links to the differences of the different products. Question 10, is there another data sources of free satellite images? I mean, other than NASA or ESA, like Brazilian or Indian agencies, what do you recommend? Yes, there are other sources besides NASA and ESA. ISRO has some good ones. CYFIS is a really good sensor that I believe they're on the 4th satellite of that mission now, and that provides, I think it's 56-meter spatial resolution, and that's accessible. The Canadian Space Agency also has a constellation of radar sat constellation, which is freely available. The coverage of that is not as consistent as other government platforms. It's more on demand, but it is freely available. So if you're looking for radar data, the radar sat constellation is also available to you. And we'll provide more links to other platforms and sensors, as well as freely available data before uploading this. So question 11, could you make some light on sun-induced fluorescence signals as it emerges as a novel indicator for vegetation monitoring? So sun-induced fluorescence or solar-induced fluorescence have been Currently, they're on a number of satellite missions, and research into this has gone back for decades. Currently, the OCO2 mission, which is flying, it's a NASA mission, OCO2, which is monitoring carbon, also has high enough spectral frequency to be able to collect SIF, or solar-induced fluorescence data. And there's another mission that just launched last year. This was a European Space Agency mission, TROPOME is the name, and that also collects the spectral frequencies there also allow for collecting solar-induced fluorescence data. The spatial resolution of such is in the kilometer scale, so it's not high spatial resolution, but it does collect data in that to be able to determine solar-induced fluorescence. There's, I think, a lot of great progress that could be worked coming with solar-induced fluorescence, as it gives a quicker response time to vegetation health than does NDVI. With NDVI, there is a temporal lag showing any stress that a crop might be experiencing, whereas sun-induced or solar-induced fluorescence, the signal from that is immediate. So the challenge now is having a space-based platform that is operational with a spatial resolution and high enough to be able to monitor vegetation at a coarse to even a moderate scale. So hopefully soon there are some missions that are coming up, and hopefully we'll post some more information of this to this question. But it's a very good question, and thanks for asking. Question 12: which are the main tools to estimate yield of crops, such as wheat, maize, soybean, sunflower, etc.? So yeah, this is a great question. Currently, the coarse resolution sensors, so MODIS and VIIRS, have been the probably the workhorses, I would say, for estimating yields for those crops, due to the crop extent of these crops, especially in the major producing regions of the world, in say Argentina and China, Australia, the United States, Canada, etc. The scale of the farmland used to grow these crops is large enough to be able to monitor it with these very coarse resolution sensors. But if you were going into a part of the world, maybe in India, where there's more intercropping, you would have to go to a higher resolution sensor. And as well as with all of these sensors, you know, if you were monitoring yield, it would be very important to have robust statistics on in situ data to be able to use the methods that are applied for estimating yields. But there's a number of literature out there, and we'll certainly include some of the links for you to read more about some of the methods and publications that have been out. So question 13, how to classify crops using Sentinel without ground data. We have just crop calendar. So that is more of a challenge. It's in situ data is very valuable in terms of accurately classifying crops. If your government or ministry or state entity has any local statistics, even or regional to national, they might be able to help if there's some type of statistics or anything on crop masking that would provide that. And if you have data from previous years, there's other literature out there that has used a time series of previous years crops grown in different regions to be able to create and model crops grown for that given growing year. So, but really in situ data is going to be incredibly important in terms of classifying, especially the accuracy of how good the classification of those crops is. So question 14, how would you determine crop type using optical data? What is the best location to determine the NDVI ranges in growing season? Um, so there's different ways of going about it. There's different uh, derivatives that you can derive from optical data, and some of those are growing degree days, and this is actually a combination of um, weather data in terms of temperature, as well as with uh, growing degree days. So this would be a combination of temperature as well as uh, the the crop emergence and how many days it takes to grow uh, to green up to flower and then to senesce. And so knowing the start of those growing degree days for your region, and some of these can be derived from remote sensing data, then uh, you can follow the you can assess what type of crop has been started within that area at that time. Um, so that's one way of assessing crop type. Uh, the best is if the important one is knowing the crop calendar for a specific region of the world. And by knowing the crop calendar and planting, then you can have some you can know if make a difference between if it's a say soy versus corn or a different crop. And this is assessed using NDVI as well as the crop calendar. Um, so question 15, what is the difference between the Landsat 8 L1 GT and Landsat uh, 008 L1 TP? These would both be level 1 products, and I don't know off the top of my head, so I cannot give an answer to this, but we will provide an answer uh, before we post this to our webpage. Question 16, what do you think about SAT cubes? Is NASA going to build one and make the algorithms free? Um, so SAT cubes are uh, incredibly valuable for crop monitoring. The temporal resolution, the high spatial resolution, the high temporal resolution. Uh, these are invaluable to accurate crop monitoring at a timely scale. Um, they're the downside, of course, is they're commercial, so there's usually cost involved with SAT cubes. NASA has launched and will continue to launch small SATs, but currently a lot of the applications are not for agriculture. NASA has really invested heavily in some of um, the platforms such as the Landsat platform and the Terra and Aqua platforms with sensors such as MODIS and as well as the VIIRS, which is the follow-on instrument to MODIS. The benefit that NASA sees in that is these are some of the most highly calibrated satellites in space. So they're really the gold standard for what other space-based platforms are calibrating to. So that's really where the investment that NASA has made in. But for the cost, definitely, because the cost of a Landsat mission obviously is exponentially more expensive than a small sat cube. So I think there's a place for both, and using both together for assessing crop health is extremely important. So is NASA going to build one and make the algorithms free? I don't know specifically for vegetation or agricultural monitoring, um, but uh, but that could be the case in the future, and I'm not exactly sure. Question 17. So while using satellite data resolution is important, so various parameters, different data from different satellites having different resolution, then the accuracy of output obtained will be less or maybe incorrect output. Is there any option to do so? Um, Using satellite data resolution is important, so various parameters, different data from different satellites having different. I don't exactly understand this question. Uh, and for the sake of time, because we're actually at 5:30, I will come back to this and see if I can understand it and give a better answer, and I apologize. I think we only have time for one or two more. So question 18, is there satellite data available that can measure soil moisture content at deeper, greater than 1 meter? Um, I need to go back. I I'm not sure. SMAP might be able to do so, or the SMOS instrument, but I can't give a correct answer for that now. But we will have a correct answer for that when we. It looks like Amita might be typing. So if Amita, if you can have anything to add to this, but if not, we'll get back to you on that. And I think we'll end it with this next question. Question 19. Which remote sensing satellite mission can be used to estimate daily crop evapotranspiration in Africa? For each of them, kindly inform on what is different, right? What is reference or potential ET, um, evapotranspiration calculation formula, resolution, sources and time range of data, levels of processing soda. Um, so I will ask just to the time if we will revisit this question on part 4 when we delve deeply into evapotranspiration, and we will provide a greater. It looks like we're also providing a link to our uh, uh, to a previous RSET training that we had before that delved into evapotranspiration. But we hope you'll take a look at that training, and we hope you'll tune into part 4, where we'll be dealing in great detail on ET products that we'll be able to use specifically for Africa. And we will provide a more thorough answer to this when we upload it to our webpage. Um, we have come to the end of this webinar, and even though we haven't addressed all the questions that we have, we will be answering them all, as well as going back and providing greater detail to the questions that have already been answered in part. So please come back to the training webpage for the RSET webpage, where we will post this hopefully within the week, so that you can gain answers as well as links to more information for all of these great questions that you asked. We want to thank everybody for joining us today, and thanks to all of the great team here at RSET for working so hard to put this training together. Do join us next week, next Tuesday, where we'll have the part 2 of this webinar series, where we'll be delving into soil moisture applications of agriculture using satellite data. So please join us next week. Thank you for tuning in. We hope you're all staying safe during this crazy time that we're living through. And yeah, thank you again, and we'll see you next week.